Thank you for the invitation to speak, the delightful introduction, and the honor you do me by actually coming and listening to what I have to say. So I'm going to try and get you a little bit excited, I hope, at least, about some of the things that we think about in the physics department here on campus. We have a whole bunch of physics going on in the physics department, but part of it is devoted to a group of us who are theorists who think about aspects of the laws of nature and how it works, and then we hand over those ideas to our experimental and observational colleagues who actually then confront that with nature and try and see, does nature really work that way? And so on and so forth. So the key thing I'm going to do, by way of a cautionary note, is warn you that I'm not just going to do the usual thing. I want to show you a little bit about what we do. So every now and again, I'm going to actually show you a little piece of a calculation to show you what we really do. We get out pen and paper. We don't just sit around drinking coffee and tossing ideas around, although we do a lot of that. But after those ideas come out, we try and shape them with the language of nature, which is mathematics. We test those ideas, we make sure they're internally consistent, so we do calculations. We get out pencil and paper, sometimes we use computers, but at the end of the day, we do calculations. So I'd like to show you a little bit about that. Now, you're probably familiar with the periodic table of elements. It's probably on a wall somewhere in your school or your department, where as a summary of one of our great achievements as a species, we've understood what stuff is made of at the level of chemistry, in the sense that we can characterize all the chemical differences between these elements in this way on this table, summarizing it. And there's structure in that table. There's patterns you've probably heard of. And those patterns are due to the fact that there's underlying structure. What makes different elements different from each other is to do with what's going on in the nucleus. So you have this little sketch of an atom here. You have a nucleus surrounded by a cloud of electrons. You've probably heard of electrons, electronics. Those are the things that move around in your phones and things like that to make them do the things they do. And deep inside there's the nucleus. And the nucleus has different kinds of things making it up, protons and neutrons, and depending upon how many of those you have in what admixture, it tells you where on the table you are. So there's some underlying structure that gives rise to that table. Now, actually, there's another table, which may or may not be on your walls, and that is because inside protons and neutrons, there's also smaller things called quarks, and there are different kinds of quarks. And these are part of what we call the list of fundamental particles. You have quarks, you have electrons. They don't seem to be, as far as we can tell, made of anything smaller, and there's a list of them. And that list of them is in another table, and that's the standard model of particles and their interactions. Now, the standard model of particles and the interactions tells you about the various particles that make up the matter that we know about, but it also tells you about how things interact through the various forces of nature. And one of the triumphs of particle physics, understanding all of this, is the realization that we can describe those forces of nature also in terms of particles. They're particles that are exchanged, and that exchange process mediates a force. And I'll tell you a bit more about that later on. But there's the table, and there's all kinds of details. There's the list of the various interactions, and there's quarks and all kinds of other things, and they all fit together. If you don't have this table in your school, maybe ask to get one. Okay, so the key point is that this is all the domain of quantum physics. These are very small things that work according to rules that took a while to figure out. The turn of the last century was when quantum physics was realized as a thing, and we now realize that nature is fundamentally a quantum place, and we just happen to live in a corner of it, a regime where most of the physics we see around us is classical. The stuff of Newton, the stuff that you know from, probably calculations you've done, where you have a ball, you throw a projectile, it moves in a certain way, you can calculate using F equals ma what the things do, and so on and so forth. Those rules you know, And I'm going to tell you them in a different way. So Newton's laws of motion can be formulated in a different way, something called an action principle. How does that work? Well, you have an object moving along with some velocity, and it has some mass. You know that. You know it has some energy associated with it. That's kinetic energy. And let's say it has that kinetic energy for a certain amount of time, which I'm going to call t. Then your calculation will tell you you can multiply them together, and there's a quantity called the action. So if you're interested in dimensions, it has dimension of energy times time, joules seconds. And that's an interesting quantity. Now, for any path, an arbitrary path moving along, there we go, we can break it up into little pieces. Even if the velocity is changing, we can break it up in small pieces so it's approximately constant on each bit, and do this action thing, and then add it all up for that path and get a number, and that's the action for that path. Okay, that's sort of interesting, because now I can talk about paths. And what I can do is formulate Newton's equations of motion in a different way, and says the path that the particle moves is the one that has the least action. Some of you may have heard of this, the least action principle. It's a different way of formulating things, and it's a very useful way of formulating Newton's classical physics, because it now helps me explain to you how to formulate quantum physics. And the key point is that quantum physics arises because nature has a fundamental unit of action. It's called Planck's constant. And you can see in the units I've written there, it's a very, very small number, 10 to the minus 34. That means that we missed it, because most of the physics we've done up until the early 20th century, the actions for any sort of processes were way larger than this tiny number. And so we weren't doing anything comparable in size to that number. But when actions are comparable in size, as happens when you have tiny, tiny particles which have tiny masses and tiny velocities, so the actions are very small, comparable to this size, then the quantum effects will reveal themselves, the quantum nature of the universe. And so you formulate physics differently in this way, but we use this language. What you do is you say, well, I'm interested in a process going from there to there. What's the probability of it being there and then later being there? You work out all the possible paths it could take. You work out the action associated with every single one of those. And you add all the possibilities together, weighted by the action in a certain way. And that's the weight that you give. It's e to the I, and then the ratio of how much action to nature's basic action do you have. So it's a calculation you can do, and when you do that, it tells you how likely something is to happen. And it works. It's spectacular, and it is, in fact, the most successful scientific thing we've ever done as a species, if you measure that success in terms of how accurately you can calculate something and then go out and test it and see that it's true. And so this is a remarkable achievement. It's all put together in the context that we're talking about now into something called quantum field theory, and you can use it to keep track of how particles interact and all kinds of things. There's a diagrammatic way, very famous sort of diagrams due to Feynman, where you say, look, there's an electron moving along, say, and it interacts with other electrons and other charged things via electromagnetism, but in this language, it interacts by exchanging a photon with it. And there's an interaction diagram for that too. And then you basically draw all the possible diagrams you can with these basic building blocks, like it's Lego or something, and actually you can model things like this electron is moving along, and there's another one moving along, and they interact, change each other's path because this one emitted a photon which was absorbed by that one. You can see this is built out of all of those sorts of things. There's rules for how much action this has, and that'll tell you the probability. But then there's additional corrections to it due to quantum physics, because you can draw other diagrams representing other paths. You sum over all possible diagrams. These are the sorts of calculations we do. And the remarkable thing is that it really works, and it's incredibly successful, as I said. So very famously, you have this 15-mile around accelerator called the Large Hadron Collider, which you've probably heard of on the border of Switzerland and France. It's the largest machine ever constructed in some sense. At various points, there are special machines, detectors, that detect the collisions of the particles that move around. You can send around different kinds of particles and calculate, if you've understood how nature works, certain kinds of particles should come out of these collisions. You calculate, and the people here will test it, and out comes the results. And the results are quite spectacular. We've discovered a lot of things this way. This is an example of one of the detectors. This is the CMS detector. We actually have also experimental physicists here in the physics department who work on this detector, design some of the components and things like that. So it's incredibly successful. And as I said, it's arguably the most successful theory in history. With computations of properties of electrons, for example, you can compute their properties to an accuracy of 1 part per trillion, and then go and test that with that precision, and test that, you know, whatever it is, 12th decimal place, and see that it's correct. Okay, well, there's all kinds of unexpected interesting benefits as well. Even nothing turns out to be interesting in this setup. So you consider the vacuum of space itself, which in classical physics is just empty, there's nothing there. But according to the calculations I was just telling you about, one interesting thing that happens is that it's actually seething with possibility. So here's a calculation. I got nothing there in this box, as it were, representing empty space. And then actually out of the vacuum, an electron and its antiparticle, the positron, which has opposite charge, pop into existence. So charge is conserved because the charges cancel, but there's some amount of mass. So you should worry about conservation of energy because I've created some mass, but let's keep going. They can dance around for a while, and then they meet each other again and annihilate and disappear. And so that's a process that can happen, and in fact is happening all over space at every point. There's some probability of that happening. Why is this allowed? Because there's some amount of energy equals mc squared, equivalent to their mass, some amount of time they can exist for before they re-annihilate. Energy times time has dimensions of action. If, again, that's comparable to the constant of nature, h bar, then it's allowed. It's essentially borrowing energy a little bit from the vacuum before it gives it back. But then there's gravity. Let's talk about gravity. So let's go back to the table, and let's look back at the list of forces. And you can see there's things talking about the weak interaction and electromagnetism and the strong interactions. These are nuclear forces and electromagnetism. And we know what the particles are that get exchanged. But let's look a little bit closer. For gravity, it says the graviton, whatever that is, not yet observed. Which means that we actually cannot model gravity so far. We cannot say that gravity is modeled by maybe the exchange of something like a graviton, like electromagnetism is modeled by the exchange of a photon. And in fact, if you work out the kinds of analogs of the theories that we have for photons, et cetera, for exchanging gravitons, it actually doesn't work. So that's a problem. We don't understand quantum gravity, and I'll get back to that in a moment. But you might go, well, wait a minute. Don't we understand gravity really well? Didn't Einstein give us general relativity you may have heard of? And that has to do with space-time being curved and warped in various ways by masses, and, you know, Star Trek and stuff like that. You've heard about warped space-time. And yes, that's a thing. Let's talk about that a little bit. Okay, so gravity, Einstein taught us, is actually geometry. And it's the geometry of space-time, which is to say that we have, I'm going to draw one space dimension. Of course, there are three of them, moving left, right, back, forth, up, down, to position yourself in space. But I'll just draw one of them for simplicity. And then there's time. Time goes by. You put those together, and it makes a two-dimensional sheet called space-time, or really a four-dimensional if you have all 3 + 1. Now, what happens? Well, that can bend and twist and change its shape. That's what Einstein discovered. And the point is that the shape changing is gravity itself, in that objects now are trying to move in this space-time, but it's curved. They're trying to follow what they think is the shortest path, and because it's curved, it looks like it's actually bending in response to the shape. So something's moving in a curved path because of the bending of space-time, not because of the force of gravity. So the Newtonian way of thinking about it is that there's a force. Here's a planet, for example, and maybe this is a satellite moving around it or past it, and the force of gravity bends its path. General relativity tells us, yes, that's good to a first approximation, but you're going to get the precise answer wrong unless you take into account the right way of thinking about it, which is that the planet, the mass, curves space-time, and then an object is trying to move in that curved space-time, and it does a bent path. And that's what gravity really is. And it sounds crazy. It certainly did in 1915 when it came out. But actually, it works spectacularly well. And we understand so much about the universe because of it. So we understand our solar system extremely well, the motion of the planets. If you just use Newton's laws, you'll get some of the aspects of it wrong, especially when they're close to the sun. The details matter, and general relativity gets it right. Famously, you might remember there was an eclipse not so long ago. Why am I bringing up an eclipse? An eclipse is useful because one of the things general relativity predicts also is that light itself gets bent by gravity. And you can calculate just how much by, and test it by predicting how much a distant star would be slightly off the position it's supposed to be if there was a massive object in front, like the sun. But you can't test that because the sun, you know, it's the sun. It's very bright. You can't look. Except if you put something in the way, like the moon. So during total solar eclipses, you can actually look and test that the stars, the distant star's light actually bends in just the way it's predicted to be by general relativity. So that's a lovely example. We've, of course, done all kinds of things. This is part of the Hubble Deep Field, the Hubble telescope, and now the James Webb telescope, and other telescopes to come. Tell us about the dynamics of galaxies, how they evolve, how the whole universe evolves. And it all works properly according to our theory of gravity. And someone's going to ask me about dark matter during the Q&A, and we can talk about that. And the whole evolution of our 13.8 billion-year-old universe, space and time itself is evolving, changing its shape according to general relativity in a way that is very predictive and can be tested by our instruments. So gravity actually works very well, despite what I said about the quantum stuff, but we'll get back to that. So one of the remarkable things is that general relativity actually predicts something quite remarkable, the thing in the title, black holes. And what are black holes? We'll say more in a moment. We'll do a calculation. But the key idea is that they're highly compact objects. Given its mass, that mass is squeezed into a relatively small space, which we're going to calculate. And that compactness has consequences. Now, when people first started thinking about them, people thought this is just too bizarre, that this can't really exist. Now we know that the universe doesn't work without them. In fact, what we'll see, let me show you, one of the discoveries is that galaxies, here's a galaxy, I showed you a field of hundreds of thousands of galaxies in one tiny piece of the sky. There are millions and millions and millions, billions in fact. By far, most if not all of those galaxies have a supermassive black hole that controls their dynamics and their evolution. Now, you probably have heard we live in a galaxy called the Milky Way, and the whole fate of that Milky Way and where we are in it and how it evolved, all of those things affects how we eventually found a home in our corner of that galaxy, etc. So knowing about black holes is, in fact, knowing something about your own origins as well, which is the "and you" in the title. So carrying on, one of the things that was discovered very early on is that black holes are important in galaxies, and they were first discovered because some galaxies are very, very active at their core. They produce jets of material that shoot out with tremendous amounts of energy that couldn't be accounted for by any mechanism known in physics except a black hole. And now there are many, many ways of determining that there are indeed black holes at the core of most galaxies, as I said. The thing we can do now, because of the Event Horizon Telescope, is actually image those black holes, those kinds of black holes, supermassive black holes, millions, sometimes tens of millions, hundreds of millions, the mass of our sun. So this is an example of one of them. This is in a neighboring galaxy. There's also images of ones in the core of our own galaxy. And what this actually is, the Event Horizon Telescope is actually a series of telescopes distributed around the Earth so that effectively the entire Earth is one big telescope. They coordinate their images, and it allows you then to do the imaging you need to peer into the core in the radio spectrum and deduce the image with a lot of digital processing to reconstruct what you see. So there's a lot to be said about that, and I'm sure you can find lots of literature about it. It's very exciting. And of course, this, some of you recognize from the movie Interstellar. This is a simulation made as realistic as possible by calculating the trajectories of all the light that would be emitted and pass by of a supermassive black hole. This is Gargantua. Some of you may have seen Interstellar. And that's what one would look like of that kind if you were out flying in space. This thing is huge, by the way. It's 100 million or so times the mass of our sun. Here is a simulation which I'm hoping is going to work of two black holes that do something that now we know is very common. They actually orbit each other. What you're seeing in that distortion is the light that I talked about from distant stars getting distorted as they pass near the intense gravity of the black holes. And these black holes are orbiting in, losing energy as they get closer and closer to each other, and they're going to merge. And look for a little ripple at the end. You see that? Now that ripple is a ripple in space-time. The geometry of space-time changes because of that event, and that ripple goes out and out and out, and if you've built the right instruments, as we have as a species, so for example, LIGO, there's one of the LIGO instruments, and there are other instruments, Virgo and others around the world, that now can detect those faint ripples in space-time itself. Now, it's a ripple in space-time. It's not like light. It's the size of space itself changing. So those two arms you see there change their length relative to each other ever so slightly as the gravitational wave goes through, and they detect that. And then they can infer that a collision happened. And they can work out by triangulating with other instruments where that happened. Here's a table of several of the events. There's one black hole, another black hole. Those are its masses, and then they merge to make that black hole. And there's a table of them that has been published, and that's constantly being updated because they've gotten so good at it. So black holes are real things. They're very active things. They're all over our universe. They're crucial to our environment in some ways, in the ways I've told you, the formation of galaxies in the universe as we know it. And they're predicted by general relativity. They're inevitable. So what exactly is a black hole? I haven't actually told you. So let's do a calculation. So time is short, so I'm going to let you fill in some of the gaps. But if you are some distance away from a massive body of mass m, like the Earth, and you have mass little m, there's a force of gravity. We could just do the Newtonian calculation, but there's a fancier version in general relativity, but this will do. And that force has an energy associated with it, potential energy. Some of you have maybe done this calculation. It's Newton's constant times the product of the masses divided by the distance away. So if I want to escape from that gravitational binding, I have to move at some velocity, and that's called the escape velocity. And so I need to associate that gravitational binding energy to my kinetic energy. So that gives me an equation. I can solve that equation, and I get what the escape velocity is. Carrying on, one of the interesting things is if I have a given mass, and I ask how much, let's say I actually did the little r I set to the radius of the object itself. So now I have a mass inside some radius r, and if I'm trying to get off that object, that's the velocity I have to do. If I shrink the radius, because you see it's on the bottom line, I have to go faster. That makes it more compact. More compact, the harder it is to get off it. Now, you probably heard that the speed of light is the fastest you can move, according to the rules of how the universe works. And so, what happens if that velocity is the speed of light? You make the thing so compact that you have to move at the speed of light to get off it. Or if it's more compact, light can't escape. Aha, that's the concept of the black hole. By the way, if you worked out the ordinary escape velocity for the Earth without doing any of that compacting stuff, it's about 11 kilometers per second. Someone can convert that to miles an hour. I don't know how to do that on the top of my head. Okay. If you work out what the escape radius, the radius of compactness for a black hole made from the mass of the Earth would be, turns out to be about 1 centimeter. So if you took the Earth, and I'll do that in a moment. I'll show you that in a moment. And crushed it down, all that mass down to the point where light can't escape. It would be about the size of a centimeter across. Sounds crazy, but nature does this. Okay, here's a really cool thing. This idea about something not being able to allow light to escape actually goes back to 1783. This is a village parson, John Mitchell, who liked to think about physics. He'd write to people at Cambridge, the famous people like Henry Cavendish at the time, and tell them some of the ideas, and this was one of them. And it was so far ahead of its time, I think people thought he was insane, at least on that point. He did lots of other amazing things too, so that was okay. Later on, Schwarzschild discovered that Einstein's equations for general relativity predicted things that we later recognized to be black holes. Oppenheimer and Schneider, yes, that Oppenheimer, realized that actually nature has ways of making them. Stars can collapse. They run out of fuel, and then they collapse under their own mass. And if they're massive enough, they'll form black holes. And modern black hole physics was born in that time. So here's the Earth. If you wanted to push it down, yes, you'd have to go down to 1 centimeter, which I don't draw on there. I stop at some point. If you did it with the sun, it'd be about the size of, I don't know, Manhattan or something like that, 3 kilometers. So a black hole is an object that's so compact that nothing can escape. And because you can't move fast enough because the speed limit is the speed of light. So that's interesting, but what about quantum physics? So this is now where we bring it all together. Because quantum physics says, well, that vacuum effect I was telling you about, where particles are popping in and out of existence all the time, is happening everywhere. It could happen next to a black hole. So what happens if one of those particle-antiparticle pairs that pops out for a while, normally would disappear, what happens if one of them falls in, past that one-way door of the horizon, the place beyond which you can't go, otherwise you won't be able to escape? Well, then the other one would fly free. And it would appear to a distant observer to be that the black hole is creating particles that are being sent out. So we now arrive at this strange situation where a black hole is actually able to lose particles through this effect. And if you do the calculation, you see it actually loses mass. And black holes will evaporate. And it looks like the first pass calculation, which was done by Hawking, it's one of the reasons it's very famous, is that there's a temperature associated with that radius called Hawking radiation, the Hawking temperature. And so black holes will lose energy through a quantum process. And one of the things is we don't know what happens. And so this is one of the things we're trying to understand. What's the fate of these black holes? Now, for astrophysical black holes, this is a very small effect. But the point is that it happens for all kinds of black holes. At least in principle, we need to figure out how to make this work. What are the real rules describing the quantum physics of these gravitational processes? And we're forced to do it because black holes really exist. They have things like entropy when you do more calculations, and you find out that they're behaving like thermodynamic objects. And thermodynamic objects normally have a different way of describing them. They have microscopic stuff going on inside them as well, right? So you take, for example, a glass of water, which has some temperature, or it has some fluidity. It has all of these nice properties that we can describe, but we ascribe those to this other description, which is to do with the tiny molecules making up water that behave in certain ways that collectively give you things like temperature and fluidity. So what's that for space-time? And that's one of the things that people work on. Is space-time made of some kind of quantum bits that we need to figure out? And what does that look like? What's the physics? So that's the search for quantum gravity that we're driven to by the two successes of gravitational physics and quantum physics. And to end then, let me just say, well, there's a possible formulation is that we, again, sum over histories. But now we'd be summing over, perhaps, summing over all possible space-times in some way. All the possible shapes that could be possible, and topologies, if you know what that is, and somehow summing over that as the quantum theory. That's a very difficult mathematical problem. We don't even know if that's the correct approach, but that's one approach that people work on a lot. It's one of the things I've been thinking about a lot recently. Anyway, if you're interested in some of the drawings I mentioned, I showed of people talking and describing physics and tossing around ideas, I actually wrote a whole book which has lots of fun things describing physics, and I drew it. It's in graphic form. You might find that interesting. The other thing I should say in closing is that a lot of these ideas, as you know, are fun to play with, the nature of space and time and quantum physics and what have you. And one of the things I love doing also is putting that out into popular culture. So you'll have seen a ton of movies that I've worked on, and TV shows and things like that, where they talk about some of these kinds of science, or they use it in their problem solving or in their battles or what have you. And that's something which is fun and hopefully inspiring. It gets you going to, you know, Google stuff, and what did Tony Stark say about, oh, go Google it. It's a thing, and you learn all kinds of interesting science that way. And I should probably stop here. Thank you.